Welcome to 2D kinematics, solving projectile motion problems. So in the last lesson, we learned about projectile motion and how we break it into the X and Y components. And now we're going to dive in and actually try to solve a couple of problems. So some of the key points of a parabolic motion problem is that the horizontal direction, there is no acceleration in the horizontal direction because the force of gravity only pulls down. Now, if there was air resistance, there would be a horizontal acceleration in that there would be air resistance, which would be a negative horizontal acceleration. But as I said in the last lesson, we were ignoring any air resistance and we're just assuming that it's a constant horizontal velocity. When solving for anything in the horizontal direction, only use the constant velocity equation. In the vertical direction, the object is always accelerating at 9.8 meters per second squared down onto Earth. So in that case, you would use one of the five equations of kinematics to solve for the variables in the vertical direction. Time is the most valuable variable when solving for projectile motion problems. This is because the time it takes to travel to a certain position will be the same for both directions, both the X and the Y direction. Time is a scalar, so it transcends the horizontal and vertical components. Basically, you don't have to break that into horizontal and vertical. It has just a scalar quantity. If using the quadratic formula to solve for time, only positive times are admissible. The maximum height, when solving for maximum height, remember that like if you have a projectile like this, right, at the maximum height, the Vy, like here, you have a Vx and a Vy component, right? But when you're at the height, you only have a Vx component. There is no Vy component because at the top of the motion, it no longer is, has it's kind of in the Y direction momentarily suspended. Like it, as you can see, as it goes up, the Y component is going to keep getting smaller and smaller until there is no Y component. And then as it goes down, because of acceleration due to gravity, it's going to keep increasing. You can use this to help you solve for the maximum height. Alternatively, for level ground only, for the total time of flight, divide by 2 to get to the time to maximum height, then solve for the maximum height. So if you are looking at the location, have the maximum height is going to occur halfway through the whole length of the projectile. So that's what this statement over here is talking about. Solving strategies. Draw a well-labeled diagram. Make 2 columns, one for the horizontal direction with 3 variables and the vertical direction with 5 variables. Fill in the known values. Make sure that the units match up. Make sure that everything's consistent, that you have everything in meters and seconds. Convert in units do not match. Stay organized, then rearrange equations before substituting in values, if possible. Keep decimal places for all calculated values until you are ready to write your final statement. Utilize the answer button and the STO, store and recall buttons on your calculator if you have those. If you're stuck, try solving for other variables to help yourself along. Time is the best variable to solve for because it is used in both horizontal and vertical calculations. Projectile motion problems can generally be sorted into one of 3 types based on the launch angle and whether the ground is level. Type 1 problems, projectile launched at an angle on level ground. So that would be like this kind of projectile. Let's see. Yes. This is a type 1 problem, okay? For this, level at ground means delta dy is equal to 0. That means that here, when it lands, it's starting at 0 and it's ending at 0. The max height occurs at half the range, right here. The maximum occurs at half of delta dx, which is at the half time. And the initial speed is going to equal the final speed. The initial speed will look like this, and the final speed will look like that, but the magnitude will be the same. So here you can go through the variables. You're going to have delta dx range, Vx horizontal speed, and time elapsed. For the vertical, you have delta dy, v1y, v2y. These are all the same. The acceleration and delta t. So you have 1, 2, 3, 4, 5 variables over here, and you have 1, 2, 3 variables in the horizontal direction. Okay, and this just goes through the strategy. So now let's do an example. A soccer player kicks a ball on a level playing field with an initial velocity of 11.3 meters per second at an angle of 35 degrees above the horizontal. Find the time of flight. So we're looking for the time, the range, which is delta dx, right? The maximum height, that would be our delta dy, and the final velocity of the soccer ball. We want V2, if you will. Okay, so here, calculating the x and y components of V1. So first thing we're going to do is we're going to break the V1 into its x and y components. So as done before, our Vx, remember we have our cosine, this is our adjacent, and this is our opposite, because this is our angle over here. So cosine of theta is going to be Vx over V1, and sine of theta is going to be V1y over V1. So if we multiply both sides of both equations by V1, you're going to get this. Vx is equal to V1 cosine theta. You can plug in the values, and that equals 9.26 meters per second. V1y is going to be V1 sine theta. You plug in the values, and you get V1y is 6.48 meters per second. Okay? So now we have, on our horizontal, we have this. We don't know this, and we don't know this, right? In the vertical, we have delta dy. We know that the ending displacement, because it starts and ends at ground level, that this is 0. We know that V1y, because we just calculated that, is 6.48 meters per second. We don't know what V2y is. We know the acceleration is negative 9.8, and we don't know delta t. Okay, calculating the time of flight using equation 3. So here we have delta dy is equal to V1. This is one of our 5 kinematic equations. And you can see that in this equation, we know that this is 0, right? We have our V1y. We know our acceleration. So the only thing we don't know is delta t. So if we plug in our values, we have 0 is equal to this, all this. So we have that. And the strategy for this is since this is 0, you can factor out delta t. And so if you factor out delta t, you have 2 things. You can have, you can set this equal to 0, or you can set this equal to 0. So we can say, oh, delta t is equal to 0, or delta t, or, 6.48 minus 4.9 delta t is equal to 0. So here, delta t equals 0. So you can see that the displacement is 0 at the very beginning of the parabola, right? That's this point. So at time 0, it's starting at a delta dy of 0, okay? Now this equation is going to tell us when it lands on the other side. So if we solve for this, we can add 4.9 delta t to both sides. We add it over here, and we're going to get and so if you solve for delta t, you have this, and it's 1.32 seconds. So if we go back up to our drawing, whoosh, we know, let's erase all this extra stuff. Lots of text messages coming through in the background. Okay, so if we look at all of this, we know that here it's times 0, and here it was time, I forget what it was. I think it was 1.32, but I don't recall exactly. Yeah, 1.32. Okay, next we're going to calculate the range. So now if we go back to our variables, we have this is 1.32. This is 1.32. So now we can just look at this and we can solve for other things, right? So we can use our single equation, which is our average velocity. Vx is equal to delta dx over delta t. Okay, we can rearrange this to solve for delta dx and plug in our values. We know that we now know our time, and we knew our velocity from above, and we get a delta dx of 12.25. Okay, next we can look at the y components here. So if we're looking over here, now we can solve for different things. We can solve for the maximum height. And so here, oopsie, where'd it go? Okay, so we know that the maximum height is going to occur halfway through, right? And so we know that the v2y, we know that the velocity at this point in the middle, in the y direction is going to be 0. We also know that the time that it takes is going to be half of the total time. So here, this is going to be 1.32 divided by 2. Okay, so we know their time is 0.66. And now we can say we can use that same equation, but we're using all the variables from the middle, right? And so we know that so here, okay, so here we plug in our 6.48 meters per second, which is our initial velocity, right? Times our time, negative 9. We put all this in and we get the maximum height is 2.14 meters. Okay. You could also use a different equation to do the same thing. So you can look through that if you want. And now calculating the final velocity, we can use this equation because now we have our delta dy. So here, if we use this equation, this is now we're back to this spot right here. So now our delta dy at this spot is 0. Okay, so that means that this whole term goes away. And we know, therefore, and we kind of know this intuitively, that our final velocity squared is equal to our initial velocity squared. So basically, it's going to be the same as our initial velocity. It's just going to be in the negative direction. Okay. So we know that our Vx stays the same. We know that our Vy is the same, only in the negative direction. So therefore our V2 is going to be the same, but instead of going in the, in this direction, it's going to be going in that direction. So instead of going above horizontal, it's going to be going below horizontal. So the soccer ball's time of flight is 1.3 seconds. The range is 12 meters, and the maximum height is 2.1 meters. And the final velocity is 11.3 meters per second, 35 degrees below the horizontal. Okay, our type 2 problems. So that was our type 1. Type 2 problems, the projectile is launched horizontally from an unlevel ground. Okay, so here you can see maybe you're launching something from like a cliff or whatnot, and here's like a diagram of that. So a lot of these problems, you have a horizontal velocity where the V1 equals Vx. It doesn't have like an angle. It's just launched straight horizontally. Okay, so this is a type 2 problem. The horizontal launch angle is 0. Okay. So it's launched horizontally from unlevel ground. So horizontally, so that the horizontal launch angle means that there is no angle, which means that there is no y component. Since if you go like this, there's only an x component. There's no y component to your velocity. So there's no need to split v1 into its components. v1 is equal to vx. The maximum height is the launch height. So this, the maximum height, is going to be where it's launched. And then here's your other variables, right? You have your theta, theta. Okay, so our delta dx is the range, our vx is the horizontal velocity, delta t is the time elapsed, delta dy is the vertical displacement, v1y equals 0, v2 is not equal 0. In this particular case, v1y and v2y are not the same. Okay, these are still the same over here. Our acceleration is negative 9.8 and delta t is the time elapsed. So on these, you solve for time using delta dy. The maximum height does not require a calculation, and use Pythagorean theorem and tangent theta to determine the final velocity. Okay, so here's an example. A stunt car is being used in a movie scene. The stunt car will drive off a 74.7 meter high cliff with an initial horizontal speed of 55 kilometers per hour. To film this stunt, the director needs to know how long the car will be in free fall and how far from the base of the cliff the stunt car will land. Also determine the stunt car's final velocity. Okay, so what they need to know is how long, the time, and how far. Okay, so these, I'm going to highlight in a different color, are the unknowns that we're trying to solve for. And up here we have the knowns, up here. Okay, so let's label everything. We have our v1, which is equal to vx. Our v1y is 0. Our delta d we have as, because it's going to be going from here down, therefore this is negative right here. Okay. We have a delta dx, okay? And then over here, our v2 is going to be, our vx is going to be the same. And this is always assuming right before it lands, not obviously after it lands, because after it lands, there would be no velocity in either direction. And this is our v2y, okay? So our v2y is basically just the speed that the car accelerated from acceleration due to gravity over the amount of time that was allowed, it had to fall, okay? So, converting v1 to meters per second. Yes, so we started off, see, we were given with 55 kilometers per hour. So if we convert the 55 kilometers per hour to meters per second, we get 15.27 meters per second. Okay, so now we can fill this in. Delta dx we don't know, vx is this, and here are the values that we have over on this side. Okay, calculating the time of flight using equation 3. Okay, so here, delta dy is equal to this. This is one of our famous, more used kinematics equation, right? And so we can plug this in. We know that our v1y is 0, so this term is going to go away. We know our delta dy, so is negative 74.7. Like I said, this term goes away. And then we have 1/2 negative 9.8 times delta t squared. You plug this in, and you solve, and you get delta t as 3.9 seconds, okay? You can't have a negative time, so we have to use the positive one. So the time that it's in the air, if we go back to here, the time it takes for it to fall is 3.9 seconds. Now, something to note is no matter how fast, if the car was going even faster or slower, it would hit the ground, whether it hit here or here or here, the time it takes to fall is going to be only dependent on this because it's the acceleration due to gravity that is pulling it down. The horizontal velocity doesn't affect the vertical drop at all, okay? So it took 3.9 seconds to fall that distance. Okay, so next now we can calculate the range. Now that we know the time, we can see how far it goes. So we can use our average velocity equation, rearrange it to solve for delta dx, plug in the values, and we get delta dx equals 59.65. Okay, now to calculate your final velocity, we can use this equation. We plug in the values we know. We know that our initial velocity was 0, so that term goes away. We plug in these values. You get a very large number, but when you take the square root of the number, it ends up being a little bit smaller, okay? And it would take the negative because it's downward, right? And so now, but that's just showing you, we don't know like the angle or anything, so we're gonna have to plug this in to solve for the angle, okay? So we know that this is that, and we know that the initial velocity is gonna stay the same. Remember, our initial velocity, if we look up here, is 15.27. So that stays the same. And so we have our components. And now we're trying to solve for the resultant. Okay, so what do we have? We have, if this is our theta, we have our adjacent and we have our opposite. So when you have those, you're going to use the TOA, right? So we know that the tangent of theta is equal to opposite over adjacent, right? And you also, from Pythagorean theorem, can do, we can say this is our A, this is our B, and this is our C. So you can do A squared plus B squared equals C squared. Or we could say VX squared plus V2Y squared equals V2 squared. We put those values in and you end up with a value of 41.2. And that makes sense because that's going to be a little bit larger than the other two values. Okay. Then we use our TOA, or tangent equals opposite over adjacent, plug those values in, and you get 68.2. So the final velocity is 41.2 meters per second, 68.2 degrees below the horizontal. BTH, I guess, stands for below the horizontal. So in conclusion, after all that work, we can say that the stun car's time of flight is 3.9 seconds. Its range is 6, they're using scientific notation, but we could also just say that this is 60 meters. And its final velocity is 41 meters per second, 68 degrees below the horizontal. Okay, and now we're going to the type 3 problems. Projectile at an angle from unlevel ground. Okay, so now this is probably the most complicated one because we're launching with both an X and Y component. So you're launching at an angle and it ends up at a lower, or it could be higher level than it starts. It's not symmetrical, so you cannot use delta t divided by 2 to calculate the maximum height. And V2 is not equal to negative V1. There's no symmetry and there's no shortcuts. Yikes. Okay, so we still have a lot of the same variables. Okay, it's just we don't have any tricks for taking some shortcuts. So here the strategy is to solve for time using delta dy. The maximum height occurs when v2y equals 0. Okay, you can use the Pythagorean theorem and tangent theta to determine the final velocity. So let's try an example. A golfer strikes a golf ball from the top of a 2.3 meter tall hill to the green below. The initial velocity of the golf ball is 28 meters per second, 45 degrees above the horizontal. Determine the golf ball's time of flight, range, maximum height, and velocity. So we are determining the time of flight, the range, maximum height, and final velocity. So we're determining 4 things. So let's fill this in. We know that this initial velocity at this angle is 28 meters per second. We know that theta here is 45. We know that the Vy component at the top is at the maximum height. once we use this to determine our Vx, we know that this Vx and this Vx will be the same. Okay. We know that our this should only go to here, right? This is our range from here to here. Here's our delta D initial as negative 2.3. Okay. And I think that's basically all the labels. Okay, so we can start off and with looking at this area up here, and we can find our Vx and our Vy components there. So our Vx component is going to be Vx is V1 cosine theta, plug those in, and you get Vx is 19.8 meters per second. Our V1y is V1 sine theta, plug those in, and that's 19.8, which makes sense because it's at a 45-degree angle, so the x and the y components are going to be identical. So if we look back up here, this is looking kind of messy now, we know that we know this component and this component, okay, is 19.8. Okay, so now we can plug those in. We know this and that. So we're starting to fill in the gaps, okay? Next, can we solve for? Well, we know this, and we know this, and we know this. So is there something we can use that involves those? Sure enough, this equation. Okay, so we plug our values into that. If you can pause and try to solve. You add 2.3 to both sides, and you end up with this. Okay, and now now we have to solve using our quadratic formula with our coefficients A, B, and C here. We can put it in the quadratic formula. Here we have A, B, C. We use this equation here, plug it in. And when you solve that, you get delta T is either equal to negative 0.113 or 4.15. And the reason you get a negative number here, think about it, is you're starting the launch from here and you end up here. So it's saying that it'll be down here at 4.15 seconds, right? Well, the negative value is going to be over on this side, right? But you can't have a negative time. So this is not admissible, but we do know that the total time from here to here would be 4.15. So the golf ball strikes the ground after 4.15 seconds. I'm looking back at this for a second. Okay. Calculating, so now that we have the time, 4.15 seconds, we can calculate the range. So we know that it's going to be in the air for 4.15 seconds, and we know its initial velocity. So if it's traveling at a certain speed, like if you're going 50 miles per hour east, and you're traveling for 2 hours, you know that you've gone 100 miles. But we can just use our average velocity equation and rearrange it to solve for the range, plug it in. Here, if it's going 19.8 meters per second for 4.15 seconds, you know that these seconds are going to cancel, and you're going to end up with a total range of 82.17 meters. Okay, moving on. It's kind of like a marathon. We are now solving for the maximum height. So we can use this kinematic equation. The maximum height, we know that the velocity v2y at the maximum height is going to be 0. So that helps us simplify a little bit. And you can arrange and solve for delta dy. You plug in the values, and you're going to get 20 meters. Now this is above the starting height, okay? So here, it's like this, right? We're looking at this height right here, okay? So the maximum height is going to be the 20 plus the 2.3. So the maximum height is 22.3. And calculating the final velocity, we can use this equation. Okay, now we know all the different components. We know this, we know this, and this. We solve, and we get negative 20.9 meters per second. So this is our V2y, is negative 20.9. We already know our Vx, so we can use Pythagorean theorem to solve for V2. Plug that in there, plug that in, and it's 28.79 meters per second. Again, now we can use our tangent of, they used alpha instead of theta. We know our Vx, we know our Vy. We plug that into opposite over adjacent, 20.9 over 19.8, and you get 46.5. Okay, which makes sense because if it was launched, what was the launching angle? I forget what the launch angle was. Yeah, it was launched at 45 degrees. So here, let's think about this for a second. It was launched at 45 degrees, right? And we know that this right here is 20 meters. And this is only 2.3. So this isn't drawn to scale, obviously. So if we were looking at it right here, this angle would have been 45 degrees below horizontal. But it had a little bit further to go. It only had 2.3 meters further to go. And in that time, the vertical component of the velocity is getting larger, right? So it's going to be dropping down a little bit more relative to the sideways. So that means that the overall angle is going to be a little bit steeper, which is 46.5. So that makes some sense. It's always good to look back and make sure that your answers seem to make sense in context. So, okay, so in conclusion, the golf ball's time of flight is 4.2 seconds. Its range is 82 meters. Its maximum height was 22 meters because it was the 20 plus the 2.3. Its final velocity is 29 meters per second, 47 degrees below the horizontal. Phew, made it through that. Any questions?